Hello, I'm Alan Bowling in the Department of Mechanical and Aerospace Engineering at the University of Texas at Arlington. And this is part 2 of the presentation on derivatives and integrals in dynamics. So let's begin. So originally in part 1 we were talking about the possibility of a mid-air collision between us moving down this path between these 2 points and our friend flying along this path to get between those 2 points. And we said in the middle we might collide if we were at the same altitude, but we have to look at the velocities that we're both moving to see if we would cross that point at the same time. So now we're trying to look at the velocity as part of this problem. So to look at velocity, we parameterize our system of equations that describe each of the lines that describe the paths that we would be flying from points A to B and point D to C, and we parameterized our position as a function of time, so we'd be able to look at velocity. So in the previous presentation, we differentiated both our parameterized equations so that we can get descriptions of velocities. And we found the velocities in the north and east direction for both paths, for our flight and our friend's flight. So the question is, how do we investigate the velocities that we have to be traveling at such that we don't have a collision? So we'll do that next. So we have the relationships between the velocities along our path, which is x1 dt is going to be equal to dy1 dt, and we have them for our friend as well, which is going to be dx2 over dt is going to equal minus 3/4 dy2 dt. So we have these relationships. So in order to investigate the relationships between our velocity and our friend's velocity, we want to go ahead and give these guys some values. So we're going to give it a fake value, and we're going to say that we're going to move, this velocity is going to be constant. So we're going to say we're going to get a constant velocity A, and both of these velocities are going to be equal to a constant velocity B. And now what we can do is integrate these guys up back to get our position information again. So we can integrate these velocity equations up to position equations. And since we know all the information about the position, like the crossing points and the starting points and the ending points and all of that, we can use that information to help us figure out the relationships between the velocities. So let's do that. We're going to integrate these guys up, all of them. So we're going to integrate from 0 to t1, which is going to be the time when they cross. And we're just going to do that for everybody. So dt, this would be 0 to t1, dt. And then I want to integrate this guy from 0 to t1, dt. Integrate this guy from 0 to t1, dt. And integrate this guy to 0 to t1, dt. And you'll notice that these dt's will cancel each other down here. So we can get a very nice integration of this. And what we're going to get is that x1 at t1 minus x1 at time 0 is going to be equal to y1 at t1 minus y1 at time 0 is going to be equal to a times t1 minus 0. So that's what it looks like for our path. And for our friend's path, you're going to get x2 at t1 minus x2 at time 0 is going to equal negative 3/4 times y2 at t1 minus y2 at time 0. And that is going to be equal to b times t1 minus 0. So it turns out we already know all this stuff. We know all the values for all of these variables, for all of these values. So let's just plug them in. So t1 is the time at when we're going to collide. So we know what x1 is equal to that. It's equal to 16/7. And our initial starting point is at 0. And for y, again, the collision, y at the collision is 16/7. And y at the time 0 is going to be 0, was our initial point. And that's going to equal to a times t1. So all you're going to get is 16/7 is equal to 16/7 is equal to a times t1. Now for our friend, x2 at t1, again, that's the collision point. So you're going to get 16/7 minus x at the initial point was point D, so that was 1. And then it's minus 3/4 times y2 at the collision point is again 16/7 minus the initial value of y, which was 4. And that's going to be b times t1. And we can go through and work this out. This is 16 minus 7/7. This is minus 3/4. And this is going to be 16 minus 28/7 equals b times t1. So this is going to be 9. It's going to be 9/7. And this is going to be minus 3/4 times negative 12/7 equals b t1. And then we just keep going. So this is going to cancel. You're going to get 3. So you're going to get 9/7 is going to be b times t1. So now, if we want to find the relationship between these two speeds, we can look at a over b is equal to a times t1 over b times t1, which is going to give you 16/7 times 7/9, which is going to equal 16/9. So we can see the relationship between these speeds is that 9/16 times a is going to be equal to b. So now you have an idea that our friend might be flying a little bit slower than us in order to cause a collision. So in summary, in this presentation we learned how to parameterize an equation of a line to incorporate the speed of movement along a line. So we're able to parameterize distance, a variable that describes the change in distance in terms of time. So that tells us how our position changes with time. And if we have that description, we can take the derivative of it to understand how to get a description of velocity, which tells us the rate of change of position with respect to time. So please watch part 2 to see how we will use this information to analyze how fast we are moving along, how fast we and our friend have to move along this curve, along our paths, to have a collision. Thank you.